Hey y'all, today we're going to be talking about the topic of partial derivatives. Now we briefly hinted at that last time when we talked about functions of several variables, but this time we're going to formalize the subject and also learn our shortcut rules. From there, we'll go on to a notion of second derivatives, which will be called second order partial derivatives, and we'll also have shortcuts for those. So, without further ado, let's dive in. Recall last time that we had the following process for measuring the rate of change in the x direction. In order to do that, we figured out the limit as h approaches 0 of f of x plus h comma y minus f of x comma y divided by h. In this case, we're tacking on the h to the x, but we're leaving y alone. And this is what measures the rate of change in the x direction. So for the function f of x comma y equals x squared plus 3y, when we actually carry out this process, we treat it a lot like a regular difference quotient. Plug in x plus h wherever you see an x, so we get x plus h squared, but leave y alone, since we're measuring the rate of change in the x direction. From there, we get some setup that looks like this. Upon expansion, we go ahead and expand out the squared and distribute in the negative. We'll arrive right over here. Ultimately, this lets us cancel out the x squareds and the 3y's, leaving us with just the limit as h goes to 0 of 2xh plus h squared divided by h, which we can factor out an h from the top, and then cancel that h, leaving us with just the limit as h goes to 0 of 2x plus h. From there, plugging in 0 gives us 2x. As I've said multiple times already in this clip, this measures the rate of change in the x direction. And for that reason, we're going to call that the partial derivative with respect to x, f sub x. This is going to denote that. Similarly, we could find f sub y. That would be the rate of change in the y direction. And this would be given by the limit as h goes to 0 of f of x comma y plus h, so putting the y or the h on the y, leaving x alone, minus f of x comma y divided by h. If you carry out that process, this will give you an answer of 3. These will be what's known as your first partial derivatives, f sub x, f sub y. As I briefly stated before, these are what's known as our first order partials. F sub x is what will denote to mean the rate of change in the x direction, and it's given by f sub x equals the limit as h goes to 0 of f of x plus h comma y minus f of x comma y divided by h. We're treating y as constant, we're leaving it alone. F sub y will denote the rate of change in the y direction. And we're going to do that, f sub y, that'll equal the limit as h goes to 0 of f of x comma y plus h minus f of x comma y divided by h, where we're leaving x alone. So we truly are measuring the rate of change in just one direction at a time. Now here are going to be your shortcuts for finding f sub x and f sub y, and this is going to be what we'll focus on for the remaining of the chapter. To find f sub x, derive everything with respect to x. That means do your power rules to x alone while treating y like a constant. So, since we're treating y like a constant, if a term doesn't have an x in it, it becomes 0. Similarly, to find f sub y, derive everything with respect to y. That means doing power rules to only the y variable while treating x like a constant. If the term doesn't have a y in it, it becomes 0. To illustrate what we mean by this, let's find f sub x and f sub y for the function f of x comma y equals 5x squared minus 2y cubed plus x. When finding f sub x, what I'll be doing is treating y like a constant. Y is no better than the number 7 here, for instance. So, f sub x. When I look at this function, I now derive every single x variable. When I derive 5x squared, I get 10x. When I derive negative 2y cubed, I notice that there's no x in there. So therefore, I treat this guy like a constant. What happens when we derive constants? It becomes 0. Last but not least, when I derive x, I get 1. Telling me that f sub x is 10x plus 1, the rate of change in the x direction. F sub y, on the other hand, can be found by deriving only the y variables while treating x like a constant. So, for instance, when deriving this guy, 5x squared does not have a y in it. X is no better than, let's say, the number 7 again, so this guy right here is just a constant. And if the term doesn't have a y in it, it becomes 0. The derivative of a constant is 0. Minus 2y cubed, we derive regularly. Becomes minus 6y squared. And then last but not least, we recognize x does not have a y in it, so it's no better than a constant, so that also becomes 0. Leaving me with negative 6y squared as my answer for f sub y. As we've seen before in our previous examples, there's no need for these two to agree. The rate of change in your x direction and the rate of change in your y direction can be totally different if you imagine yourself standing in a wave pool like we did last section. To further illustrate this concept, because it can be a little confusing right away, let's go ahead and dive into more examples. Let's dive into more examples. Find f sub x and f sub y for the following functions. Now admittedly, part A is definitely a little bit more involved than part B. However, part A can be pretty enlightening. So let's start with it. Remember that when we're finding f sub x, we are treating y like a constant and we're only deriving the x term. So when I approach something like 6xy, how I like to do it would be copy down everything that's not the x and then derive the x term. Y is no different than a constant. So this thing becomes 6 times 1 times y. I derived only the x term. The y survives in this case because it's attached through multiplication. Moving on, I derive the x term, giving me 2x times y. Yet again, the constant y in this case survives. Plus 8y squared does not have an x to it, an x attached to it. So this thing is no better than just a regular constant, so it becomes 0. There's no x attached to it. Last but not least, x to the 5th becomes 5x to the 4th, as normal. Upon simplification, this leaves me with 6y minus 2xy plus 5x to the 4th as a final answer for f sub x. To find f sub y, we treat x like a constant while deriving the y variable. So when I approach the term 6x times y, I copy down everything that's not the y term, 6x, and then I derive the y term, giving me 1. Moving on, I have the same approach with x squared times y. Copy down the non-y terms, which is just x squared in this case, and derive the y term, 1. 8y squared we can derive regularly with respect to y, giving me 16y. Last but not least, this x to the 5th term does not have a y attached to it, so it is no better than just a constant, so therefore when I derive it, it becomes 0. Upon simplification, this gives me 6x minus x squared plus 16y. I really think that copy down the non-blank terms, so in this case the non-x terms, and then deriving the x is a really good strategy. Approaching this one below, now a lot simpler. When we find f sub x, remember we're treating y like a constant and we're deriving the x variables. 2 really is just a constant, So that one just becomes 0 for f sub x. 4x squared we derive regularly, giving us 8x. And then last but not least, the negative 3y does not have an x attached to it, so that goes away and becomes 0. It's no better than a constant, giving me 8x as an answer. F sub y is found by treating x like a constant. So 2, just a regular constant, still becomes 0. 4x squared does not have a y attached to it, so that is no better than a constant, and therefore, upon deriving, becomes 0, since we're holding x constant when we're deriving with respect to y. Last but not least, minus 3y will end up becoming minus 3, giving me, as an answer, negative 3. The trickiest part of this section is going to be convincing yourself that holding y and holding x as constants is acceptable, and how to do this in an efficient manner. I really believe in copying down the non-blank terms, so in this case the non-x terms, and then deriving the x variable. Or in this case, copying down the non-y terms, and then deriving the y variable. Let's get into more examples. To further hammer home the point of holding one variable constant while deriving the other, let's consider the function f of x comma y equals 5x cubed times y to the 4th plus 10x squared times y cubed plus 3x squared minus 7y. When finding f sub x, derive the x variable while holding y constant. So while I approach a term like this, I copy down the non-x terms, and then I derive the x term, giving me 3x squared. Over here, I copy down the non-x terms, 10 and y cubed, and I derive the x term, 2x. By the way, the reason we're copying it down is kind of like we do with constants. If I were to derive a little tangent right here, if I were to derive 3x squared regularly, we all know that one just becomes 6x. However, when we were first learning it, we took the side step of copying down a constant and then deriving just the regular x, which then simplified upon multiplication. We're doing a similar thing here. So that's why we're just copying down these terms. Back to the derivative, we have 5 times 3x squared times y to the 4th, copy down the non-x terms and derived x, plus 10 times 2x times y cubed, plus, since we're deriving with respect to x, 3x squared just becomes 6x. Lastly, minus 7y does not have an x in it, so it is no better than a constant, so it just becomes 0. We can just go ahead and leave off that 0, giving us our answer of, I'll go ahead and actually write it, giving us an answer upon simplification of 15x squared y to the 4th plus 20x y cubed plus 6x. Lastly, if we go ahead and find f sub y, we will now hold x constant while deriving the y term. Copying down my non-y terms, 5x cubed, and then deriving with respect to y, I get for the first term 5x cubed times 4y cubed. The second term, copying down 10x squared and then deriving y cubed, gives me 10x squared times 3y squared. The 3x squared does not have a y in it, so it's no better than a constant, so it goes away upon deriving, plus 0. Lastly, the minus 7y, we derive regularly, becomes minus 7. Upon simplification, my answer will be 20x cubed y cubed plus 30x squared y squared minus 7. Just like with regular deriving of one variable, once you guys get good at it, you won't really need to do this step, and you'll be able to just kind of hop straight to here and just do the multiplication in your head. However, to start off, I strongly recommend copying down the non-blank terms, so here are the non-x terms, and then deriving the x term, and then simplifying it out. Now, it is huge to note that just because we have a new way of deriving doesn't mean your old rules die. Therefore, these rules, the product, quotient, chain, log rule, and exponential rule, still occur and have their day in the sun. We just derive the x or the y variables as we learned in the previous slides. So let's consider the following example. Find f sub x and f sub y for the function f of x comma y is equal to the square root of x squared minus 2xy minus y squared. Now, this setup, as we have a big square root, is definitely a chain rule scenario. And in fact, we still use the chain rule. The first thing we usually did was convert this to a fractional power. And that does not change. So now let's go ahead and find f sub x. As we stated before, this is definitely a chain rule situation. So the derivative of the inside times the derivative of the outside still persists. The derivative of the outside, going in this order, would be 1/2 times the entire inside, x squared minus 2xy minus y squared, all to the minus 1/2 power, the derivative of the outside, times it by the derivative of the inside. And this is where our other rules start to play in. The derivative of x squared, as we're deriving with respect to x, is just 2x. The derivative of minus 2x times y, I copy down the non-x terms, 2 and y, and I derive x, giving me 1. Lastly, minus y squared does not have an x in it. So since we're deriving with respect to x, it is no different than a constant, so therefore it becomes 0. The derivative of the inside, giving me a final answer, if I like to simplify it, of 1/2 x squared minus 2xy minus y squared to the negative 1/2 times 2x minus 2y. Ultimately, I could distribute in that 1/2 over here, since this one, I can't do it right here because it has a power, giving me a final answer if I also bring this to the bottom of x minus y, the 1/2 will cancel out with the 2's, divided by the square root of x squared minus 2xy minus y squared. Go ahead and pause the video right now if you want to see this, as just because I need more room, I'm going to erase it. Now, in order to find f sub y, we still have to respect the chain rule. So, f sub y is equal to the derivative of the outside, 1/2 times x squared minus 2xy minus y squared to the negative 1/2 power, so that part stays the same, times the derivative of the inside with respect to y. The derivative of the inside with respect to y, well, since there's no y term there, it's just a constant. That's how I'm viewing it. So the derivative of x squared is 0 minus, copy down your non-y terms, 2x, and derive your y term, times 1, minus, derive this regularly, giving me 2y. The derivative of the inside with respect to y. Upon simplification, this side will just become minus 2x minus 2y. And last but not least, we could distribute in the 1/2, canceling out these 2's, and make this into the bottom. Move this to the bottom, giving me an answer of negative x minus y over the square root of x squared minus 2xy minus y squared. Sometimes you'll see the book, for instance, if this were in the book, you might see the book write the top, minus x minus y, as negative x plus y in parentheses. Let's dive into more examples where we use other rules, other than just the chain rule. Find f sub x and f sub y for the following functions. Let's start over here. F of x comma y equals the natural log of x plus y divided by x minus y. Now, just like our logarithm section, it's going to pay to simplify this via some algebra. Just because there are two variables doesn't mean we can't do that. Since I have division on the inside, this will simplify to subtraction on the outside. The natural log of x plus y minus the natural log of x minus y. That's all the simplifying that we can do. From here, notice that we're going to have two log rules. The log rule persists. The derivative of the inside divided by the original inside is our rule for finding the derivative of a logarithm. So f sub x is going to equal the derivative of the inside of this first log. Well, we derive our x term, since we're deriving with respect to x, and we get 1. But when we derive our y term, since there's no x attached, we get a 0, divided by the original inside. Minus the derivative of the inside with respect to x is just again that 1 plus 0, or excuse me, 1 minus 0, same difference I suppose, divided by the original inside, x minus y. So the logarithm rule still persists, ultimately giving me an answer of 1 over x plus y minus 1 over x minus y. You could combine that into one fraction, but that's good enough. If I now derive this with respect to y, the logarithm still persists. That log rule, excuse me. The derivative of the inside with respect to y divided by the original inside. The derivative of the inside with respect to y will just be 1, as the x will go away, divided by the original inside of x plus y, minus the derivative of the inside with respect to y, so we get a negative 1 right here, a little bit different, divided by the original inside, x minus y. Upon simplifying, we get 1 over x plus y plus 1 over x minus y as our final answer for the derivative with respect to y once we go ahead and cancel out those negatives. This one over here is going to be a little bit sneakier. The function f of x comma y equals x times e to the x plus y. Now allow me to emphasize that times. When finding f sub x, notice that I have two terms regarding x. I am treating y like a constant. If it helps, in my head when I'm finding f sub x, I'm viewing this function as no different than x times e to the x plus some constant, let's say 2. If I were to derive this thing with respect to x, I would need a product rule. And hence, I do need a product rule right here. So first d second. First is just x. Times d second. Here we have an exponential. To derive an exponential, you derive the power and multiply it by the original thing. The derivative of the power with respect to x, the x will become a 1, and the y will go away. So the derivative of the power becomes 1 times the original function of e to the x plus y. First d second. Plus second e to the x plus y times d first. The derivative of x with respect to x is just 1. Ultimately leaving me with the answer of x times e to the x plus y plus e to the x plus y, which you might see written after factoring out e to the x plus y as x plus 1 times e to the x plus y. It's a product rule because we're deriving with respect to x. And I have two terms regarding x. When I derive with respect to y, however, this becomes a different game. Instead now of viewing this function as something similar to this, as when I derive with respect to y, I'm treating x like a constant. I view this function, since x is now a constant in my head, as no different than 2 times e to the 2 plus y. The x just becomes a constant for us in our eyes. So therefore, you don't necessarily need a product rule for this anymore. And we could just say, well, the derivative of this guy, copy down the non-y terms, so x, and then derive the exponential with respect to y. The derivative of the power with respect to y is 1. So technically I'll write it as 0 plus 1 because x will go away, times the original function. Which gives me an answer of x times e to the x plus y. Now, if this was confusing to you, don't worry. You could still treat this like a product rule if it makes you feel better. So kind of in an alternate universe, let's go ahead and treat this like a product rule to prove our answer. And we would derive it with respect to y. So, to treat it like a product rule, we would say first, so x times d second. Well, d second will end up just being 1, or 0 plus 1 times e to the x plus y, the derivative of the power times the original function. So first d second plus second e to the x plus y times d first with respect to y. The derivative of x with respect to y is 0. This leads us to cancel out this entire term. And ultimately, we notice that these guys are the same. This would give me an answer of x times e to the x plus y as well. So if you don't feel confident or treating x like a constant right there, your product rule will lead you to the same answer. However, it's just not as quick. Now, as before, we're able to find more derivatives than just our first order partials. I'm going to use blue to indicate deriving with respect to x, and red to indicate deriving with respect to y. Blue means you're treating y like a constant, red means you're treating x like a constant. So, let's start with a function f of x comma y. We could derive the x variable to land on f sub x, and derive the y variable to land on f sub y. These two are just both functions of x and y. So therefore, I'm allowed to do the exact same split with both of them. If I derive f of x with respect to x, I get f of x parentheses x, which, since we're lazy, we're going to write as f sub xx. If, however, I derive this with respect to y, I get f of x derived with respect to y, or f of xy. Similarly down here, I could derive this with respect to x, giving me f sub yx, or I could derive this with respect to y, giving me f sub yy. You read this in order. I derive first this guy, then this guy. First this guy, then this guy. So f sub yx means I first derived with respect to y, and then I derived it with respect to x. Now these two will end up being equal in every single case that we're going to consider. However, you still want to go ahead and find them. So without further ado, let's go ahead and dive into some examples as to getting these 4 second order partial derivatives. Let's begin with the following example. Find f sub xx, f sub xy, f sub yx, and f sub yy for the function f of x comma y is equal to x cubed minus 4y squared plus 7x minus 3. I could have also stated, find all 4 second order partial derivatives, and that would have mean asking the same thing. Well, in order to get these guys, I have to go through the first order partials, just like with our deriving of functions of one variable. So first and foremost, let's get f sub x. I will be deriving the x variable and holding y constant. This gives me 3x squared. No x is present here, so I get a 0. Plus 7x, so that thing derives to be plus 7. And then the constant goes away. F sub y follows a similar fashion, except for now we're deriving y and holding x constant. So since no x or no y's are present on these three terms, we'll get zeros for all of them, leaving me with just negative 8y. From here, go ahead and derive, with respect to each variable, each function. So f sub x, if I derive f sub x with respect to x, f sub x with respect to x, I get 6x, and that goes away, the constant goes away. So just 6x, deriving this with respect to x. If I derive f sub x with respect to y, finding f sub xy, notice that there are no y's present in the entire first order partial f sub x. Since there are no y's present here, I get 0. Finding f sub yx, meaning deriving f sub y with respect to x, as there are no x's present in this, I also get 0. Last but not least, deriving f sub y with respect to y gives me negative 8. These are my 4 second order partial derivatives. Let's do one more example to round out the day. Find all second order partial derivatives for the function f of x comma y equals x to the 4th minus 2x cubed times y squared plus 3y to the 7th. In order to find these second order partials, we need the first order partials. Let's first off get f sub x. Derive this guy with respect to x while treating y as a constant. X to the 4th, therefore, becomes 4x cubed as regular, minus, copy down the non-x terms, and derive the x term. So minus 2 times 3x squared times y squared. Last but not least, this guy does not have an x in it, so it becomes 0. Upon simplifying, what I get is 4x cubed minus 6x squared y squared. If you get good enough, then you can just hop straight to this line, go for it. This is the safer approach. F sub y can be found in a similar manner, except for you're deriving y and treating x as a constant. X to the 4th does not have a y in it, so therefore that becomes 0. Copy down the non-y terms, so minus 2x cubed, and then derive the y term, times 2y. Last but not least, this one is derived as regular, plus 21y to the 6th. Upon simplifying, we land on negative 4x cubed y plus 21y to the 6th. If you can get straight to this line, go for it. This is the safer approach. Now, in order to find our second order partials, we just derive each of these with respect to both x and y. F sub xx, deriving f sub x with respect to x, gives me 12x squared minus, copying down the non-x terms, and then deriving x will give me minus 6 times 2x times y squared, for a final answer of 12x squared minus 12xy squared. Feel free to factor out a 12x if you wish, otherwise that's good enough. F sub xy, deriving this guy with respect to y, gives me a 0 in this term because there are no y's present. Over here, I copy down the non-y terms because I'm deriving it with respect to y, and then derive the y term, times 2y, giving me an answer of negative 12x squared times y. this right here is my f sub xx, while this right here is my f sub xy. To find f sub yx, derive f sub y with respect to x. When I derive this with respect to x, I copy down the non-x terms. Give me some room right here. And I derive the x term, 3x squared. Notice that the second term does not have any x's in it, so I get a 0. Ultimately giving me an answer of f sub yx equals negative 12x squared times y. Lastly, to find f sub yy, derive f sub y with respect to y. Copy down the non-y terms, negative 4x cubed, and then derive the y term, times 1. In the right hand, 121y to the 6, derive that regularly as we are deriving with respect to y. What we'll end up with is 126y to the 5th power. This will be f sub yy. That's how we're going to be able to find our second order partial derivatives. Hey y'all, thanks for tuning in today as we discussed our partial derivatives. Now you might have been wondering the entire time, why do we call them partial derivatives? Well, it turns out we're only deriving part of the problem. So, as a recap, f sub x measures the rate of change of f in respect to the x direction, while f sub y measures the rate of change of f with respect to the y direction. They have no obligation to be the same. To find f sub x, derive your x variables while treating your y's as constant. F sub y is found in a similar manner, except for you'll be treating y as a variable and deriving it, while treating x as a constant. Finding your second order partials is as easy as just deriving your first order partials in both with respect to x and with respect to y. Last but not least, if you are finding a more complicated partial derivative, respect your previous rules. The chain rule, product rule, quotient rule, logarithm rule, and exponential rule all still apply, except for the fact that we'll be deriving with respect to x and y on the inside of them. So, go ahead and try your homework, email me with any questions, and last but not least, thanks for watching.